are you fine that I let the people ask question?
Sure. During the talk, you mean? No problems. Yeah.
Okay.
So I put a timer for myself, let's say at because I thought it was a summer school, so I have a broad introduction.
It's both, so but it's good. So there are a lot of students, so it's good if you make a broad introduction.
Okay.
And you can look at the bottom now, the number of participants. So you see that now it raises very fast.
No, I don't. Since I'm playing the screen, I don't see any bottom.
Okay.
In fact, are you going to monitor the questions? Because I don't have any toolbar here, because I just see my...
Yeah, we'll do this.
Okay, good.
I had problem to be in the last talk, so but now I learned how to do it.
Yeah.
So, hello again. So we will listen now the second talk of today by Marco Polini from the University of Pisa. And again, so if you have question now, I understood how it works, and so I will give you live so that you can answer directly the question. So Marco, please start.
Okay, good. Okay, so good afternoon, everybody. It's very weird, not seeing people in the room, but okay, it is what it is. So, today, so as Adrian said, I moved from IIT to the University of Pisa from January 1st, and today I'm going to talk about something that was really pioneered by the ICFO guys, by Frank Coppens and collaborators. I will acknowledge them in just a second. I am everything but an expert in the field, so I'm learning a lot of new things. So I'm going to talk about some experiments and our theory interpretation. The experiments have been done at ICFO on samples by Pablo Arillo Herrero, done at MIT, and it's essentially light matter interactions. So you see there is this beautiful image here. It's a cartoon. But there is the tip, and probably Dmitry Bazov already talked a lot about this. So it's a scattering, scattering type, scanning near field optical microscopy. Essentially, there is a metallized tip of an AFM, and you shine focus infrared light in it. And because the tip actually breaks translational invariance, you are able to couple far field photons to collective excitations in the electronic medium, in this case, a twisted bilayer graphene. But so I'm going to give you a broad introduction on how this tool was used in the past, let's say 10 years or so, to study two-dimensional materials, in particular simple, basic graphene, and then I will talk about new results coming out from the ICFO lab and the theory collaborators. So yeah, so this is something I always forget. It's many thanks to the organizers of the workshop, and as Frank said, it's really great to reach out so many people despite the hard times we're going through. So thank you very much for putting this up. It's a lot of work. But the main actors here, and you see we have a rugby player from ICFO. He was a former student of mine. He easily recognizes the rugby player. Is Jacopo Torre, and he's now at ICFO working with Frank, and a PhD student of mine, Pietro Novelli, was essentially about to finish and defend his thesis. Those are the main guys that did calculations on the theory part, and then on the experimental part, I had the luck to interact with very young and strong guys. Niels Esp, who gave already a talk, actually, a hot topic talk a couple of days ago on this. So I'm going to expand on what Niels said, and as I said, everything was pioneered by Frank Coppens in collaboration with Pablo Aurelio Herrero. These are a couple of papers. My only two papers on twisted bilayer graphene, and those are on the archive. And I'm going to talk about these papers. So the first question in this conference is probably why would you be interested in optics when the most cool things, experimental wise, have been clearly seen in transport. Okay, so we have heard a lot during these days, and all I heard was based on transport. But the key point I want to convey today is that there are other tools, of course, when you allow a finite incoming frequency of your probe. In this case, infrared, mid-IR. Light, there is these new things that you can probe. In fact, it doesn't take a genius to understand. We have seen these band structure plots over and over these days, but clearly, when you have far field light coming in with a finite frequency in the mid-IR, you are going to couple the manifold of flat bands to the remote bands, and we have already heard several times, starting from the very first day in the talk by Alan, that we have heard how crucial those remote bands are. So gaining information on the dispersion and energy scales, separating the remote bands, the manifold of flat bands from the remote bands can play a big role. And so the claim is that we will able, by doing the studies that I'm going to talk about, we are able to access parameters which are difficult to extract with other tools. And certainly this is a complementary technique, allowing you, for example, to extract parameters as the ratio between the intra, let's say, sublattice tunneling parameter and the inter BA sublattice tunneling parameter U1, and I can't do better than the other speakers stressing how important those parameters are. So that's about far field optics. Of course, as I will mention at the end of the talk, I'm a theorist, but I understand that doing experiments in the far field requires having large, high-quality samples, and that's not yet possible. So we will use these nanophotonic, nano-optics tool based on these SNOM apparatus, and that allows you, as I said, to measure also collective excitations. And why would you be interested in collective excitations? Again, I was very much inspired by talks in the last few days. Just to give you a couple of examples, Alan, for example, mentioned that these linear in temperature resistivity may be explained by inelastic collisions between electrons and collective modes of the broken symmetry states. So having eventually an apparatus that works at low temperatures will allow you to probe these collective excitations of the broken symmetry states. That's an example. Another example is that knowing the collective modes of the broken symmetry states will allow you to enables us to understand and assess the reliability of many body theories. And an example was, a very nice example was given also by Vishwanath yesterday, I believe, where his theory, for example, on the Kramers intervalley coherent phase supported Goldstone modes and with linear dispersion. So hopefully when technology will allow to to put the tip of the AFM in a cryostat and go to very low temperatures, which is something that a number of people in the world are working on. We will also be able to assess complicated many-body theories for this strongly correlated problem. But this brings me immediately to the first disclaimer of the talk. I have 3 disclaimers. I believe we have, taken a very humble approach here. The problem is complicated enough, and even knowledge on the details of the single particle Hamiltonian is still unclear. So imagine, the calculations based on many-body, including many-body effects. So our humble approach was to, begin from high-temperature physics and essentially carry out studies of the collective modes and the optical conductivity of twisted bilayer graphene in a wide range of twist angles at room temperature, because that's where SNOM is currently available and has been tested over and over to do very interesting physics that I'm sure Dmitry Bazov talked about. And although, as I said, Dmitry, Alexei Kutsmenko, Frank Coppens, and many others around the world are working on developing cryo-SNOM. But today it's going to be about really room temperature physics or high temperature physics, away from all the broken symmetry phases which have been mentioned in these few days. And again, apologies, since I'm not a founding father of the field, but just a follower. I'm sure there are many, several papers certainly also on optical and plasmonic properties of twisted bilayer graphene. This is a quite complete list, I believe, but I may be forgetting somebody, so apologies for that. In the papers you find many more probably, and I hope that's fine with you. Okay, so let me begin with my introduction, okay? And what do I mean by collective modes? And I'm sure Dmitry has done a great talk. I was not able to attend because I was buying a house, and I already apologized with him for being out of my small house here. Let's start from the simplest possible collective mode. We are talking about physics of 1950s, Bohm, Pines, Gell-Mann, Bruckner, very simple excitations in a metal, collective density oscillations that occur in an electron liquid. These guys are called plasmons. Essentially, when there is an external disturbance, electrons move to screen out the external perturbation, but they typically tend to overshoot the mark, and they are pulled back by a restoring force. So it's physics really like Hooke's law. Since I'm teaching classical mechanics now, it's really, there is a restoring force. You know that when there is a restoring force here provided by all the electron system, there is also an oscillation. And so these oscillations of the collective density of an electron liquid are called plasmons, have been studied over and over by a variety of experimental tools. Theoretically, you study these things usually by using a Kubo linear response theory. So again, late 50s. So you introducing the concept of a so-called density response function, chi-n-n, written here in the frequency domain, finite frequency omega, representing the frequency, for example, from the time-dependent electric field, or vector potential coupling to density, and I'm using a real space representation that will be used later for twisted bilayer graphene, which is not Galilean invariant. So the first part of the talk is essentially on plasmons in Galilean invariant electron liquids, like graphene was essentially Galilean. Well, it's as a continuum model, essentially valid for a broad energy range, and then we'll move on to study the density response function of finite frequency for twisted bilayer graphene. So there's an external potential, and the system responds with a density delta n of r and omega, and if the external perturbation Vx is sufficiently small, you can apply linear response theory, and delta n is linked with the external potential by the equation written here in the slides. Okay, there is a more useful tool in many-body theory, which is called the proper density-density response function. Chi tilde here, just to make a distinction with the causal retarded response function chi. So chi tilde is the response of the density delta n, but not to the external potential, but to the self-consistent field, the R3 field, the sum of the external potential and the internal total field, which is the R3 self-consistent field. So chi tilde is defined in equation A, essentially. So chi tilde links delta n with the screen potential, and the screen potential, as I said, it's the sum of the R3 field, so depends self-consistently on the density and the external potential. Plasmons do not require external pumping, so they occur also in the absence of an external potential, and they are self-sustained oscillations because there is this Coulomb restoring force. And so you can plug equation B in equation A essentially and get a complicated integral equation for the plasmon wave function essentially, which is the screen potential. And that's written here in general for an inhomogeneous system. And so the solutions of these integral equations are called plasmons, and they are particularly easy to find in a celebrated approximation, which, as I said, it's was pioneered by Pines, Bohm, Gell-Mann, and Bruckner in the late 50s, and everybody is a textbook theory. It's called the random phase approximation. You don't see random phases here, but in a certain derivation of this theory, you will see those. And in this approximation, the proper density-density response function chi tilde, which is in fact the sum of an infinite sum of Feynman diagrams, which are called indeed the proper diagrams, it's brutally approximated with the density-density response function of a non-interacting system. Chi zero, that's the notation here up in the slide. Chi zero is the simple density-density response function of the non-interacting system. So for a translational invariant system, convolutions in real space that I was showing earlier become simple algebraic products. And so you can close these RPA equations very easily in systems with translational invariance, and you get that the density response is proportional to, so the Fourier components of the density response are proportional to the Fourier components of the external field, and the proportionality coefficient is the density-density response function. And as I said, well, as you see here, there is a denominator in this equation. So self-sustained oscillations, plasmons, in this case of simple metals or conductors like graphene, are essentially, mathematically, they are poles of the density-density response function occurring infinitesimally below the real axis in the omega q plane. And so let me talk about the workhorse of SNOM, okay? So the material where SNOM has been probably most successfully applied in the last 10 years by a variety of groups that I will mention. And, let's target very well understood material like graphene in the Fermi liquid regime. And this supports plasmons which are, intra and excitations, usually called in the literature Dirac plasmons, okay? So you set up this machinery of linear response theory and a random phase approximation, and in order to understand what's the dispersion relation of these modes, you can use a projected F-sum rule, essentially, that says that for small q, so in the long wavelength limit, and for frequencies omega, which are smaller than the Pauli blocking gap, which is twice the Fermi energy in units of h bar, but frequency much larger than the threshold VFQ for single electron hole excitations, this density-density response function of the non-interacting electron system can be very easily approximated by density of electrons and q squared divided by an effective mass, usually called cyclotron mass. Effective mass is a density-dependent mass, and omega squared. And in fact, everything is controlled by the proportionality coefficient of q squared over omega squared, which apart from a factor pi e squared is called the Drude weight of the theory. So in a gallium arsenide quantum well, the effective mass would be constant given by the crystal, and in graphene this is density dependent, and this Fermi liquid approximation works very well for the range where plasmons are low loss and long lived. So if you look for the zeros of the denominator of the response function that I was mentioning earlier, you can immediately solve this very simple equation, and you find something which is essentially nowadays textbook. You find that plasmons in a two-dimensional conductor, intraband plasmons in a two-dimensional conductor, they scale like the square root of in-plane wave vector Q. So they are sensitive, of course, to the dielectric environment. So epsilon bar 0 is a static dielectric function taking into account screening of nearby dielectrics. So in second generation samples, for example, screening from hexagonal boron nitride crystal slabs, you can include whatever you like. You can go beyond this long wavelength limit. You can do all sorts of manipulations on the RPA theory that I was mentioning earlier, but that's essentially the essence. And so you immediately see that you have a so-called photon mismatch momentum. So if you want to excite these guys, these collective excitations, they carry a finite momentum Q on the order of a good fraction of the Fermi momentum Kf, and so you have a problem, right? The far field photons coming in with essentially zero wave momentum can't couple to collective in-plane excitation. So there are a number of ways to bypass this problem. You can deposit a grating coupler on top of your 2D material, or you can use this beautiful technique pioneered in a case of graphene by Frank and Dimitri. Those are the two probably most relevant references in historical references. And so the idea is that essentially the tip, as I said, has a radius of curvature, let's say 1/20 nanometers, as a form factor that couples with graphene plasmons, and just by shining mid-infrared light, for typical carrier densities, you can excite these collective modes. They, go and travel. They are propagating plasmons. They reach the boundary of the device. They are reflected back, and they are out-converted back into photons by the same tip that launched them. And so by collecting photons, you are essentially able to produce interference, look at the interference fringes in real space and measure the plasmon wavelength. So 2 pi divided by the plasmon momentum Q at a fixed frequency, which is given by the laser you're using in the lab. And so you're able to test, for example, this very simple RPA prediction. And, a lot of excitement in the field historically was due to the fact that the plasmon wavelength tends to be much smaller than the free space illumination wavelength. And that's, something that people of the Plasmonics community like a lot, because you can compress electromagnetic energy into small, nanoscale devices. And so this trick was particularly, this property was particularly used. And so we are talking about, compression factors, lambda PL in units of the free space illumination wavelength of 140, 1/50 in these historical papers. And people also looked at the very beginning, these historical slides are on first generation devices. Graphene was deposited either on silicon dioxide, very rough substrate, rich with charged trapped states, and or on silicon carbide. But the main thing is that they are quite lossy. I mean, nothing compared to, for a comparable compression ratio, nothing compared to how lossy a noble metal is, so much less lossy than a noble metal. Plus they are, tunable, because you can change by electrical field effect the density in your 2D system. And so you can achieve, a broad spectral range by just doing electrical field effects. But we are talking about lifetimes on the order of 30, 40 femtoseconds. You see these from the small number of fringes that you can see in these early experiments. Okay, so a mini revolution happened. As for the transport people, they were very excited when they realized that you could minimize disorder by encapsulating graphene in boron nitride. So it was pretty clear that this was going to work also to increase the plasmon lifetime. And so Frank and collaborators in 2015 carried out these mid-infrared experiments in encapsulated graphene. You see spectacular, these this number of fringes has increased a lot, and so plasmons propagate over much longer distances compared to first generation devices. And so just to make a summary, essentially we are in 2015 roughly with this slide, and you could reach in encapsulated graphene compression ratios of the order of 1/150 with lifetimes approaching 1 picosecond. And later on, just a couple of years ago, Dmitry Bazov showed that, for example, you can go also to relatively low temperatures. I believe the experiments in this Nature paper were carried out at 60 Kelvin, and you could achieve their, much longer lifetimes, of course, because the main agents scattering graphene plasmons as pretty much as, electrons are acoustic, gauge phonons essentially, and so you can quench those by working at low temperatures. Just to bring you up to more recent years before I begin, studying twisted bilayer graphene. So you have the possibility also of going down to the terahertz, which is interesting in condensed matter physics, because a lot of excitations in strongly correlated materials are in the terahertz range. And again, graphene in this case worked as a fantastic workhorse, as proof of principle that you could do these nanoscopy experiments in the terahertz domain. You have to do a little bit of tip engineering, but from the fundamental physics point of view, you can do a very simple trick to make sure you have long-lived plasmons in the terahertz domain for working still with ordinary carrier densities in graphene. And the trick is to screen long-range Coulomb interactions by placing nearby gates. So by placing this LG1, LG2 split gate near graphene, let's say 5 nanometers, and then Frank and collaborators push this to 1 nanometer, 3 layers of boron nitride separation between the split gate and graphene. You can essentially morph the plasmon dispersion from an ordinary square root of Q into an acoustic plasmon. It's a gapless mode, which then carries a very large for fixed excitation wavelength omega, it carries a much larger momentum, in-plane momentum Q. And then you can do simple modifications of your RPA theory to take into account screening of the nearby gates. But the point is that at a given omega, in this case, a few terahertz, you are able to probe long-lived modes with large in-plane momentum. And since technology is not our main focus here, but theoretical physics, having these excitations with large Q allows you also to probe sophisticated non-local effects. In other words, for the students here, RPA is a very simple, quasi classical approximation that takes into account the fact that when the electron fluid responds to an external field, it creates polarization charges, okay, as pretty much as a dielectric. But as we know from the theory of Clausius-Mossotti of dielectrics, even in an electron liquid, there are short-range local field effects, which are completely, quantum mechanical. Think about, simple Pauli principle that forbids two electrons with the same spin, of sitting on top of each other. And so, modes with large Q allow you essentially to probe fundamental physics. And we were able a couple of years ago to probe effects that had been probed by a variety of different techniques, in particular, Shubnikov the gas transport, for example, and scanning SET experiments, probing the compressibility. We were able to essentially measure the same physics, access the same many-body physics in single-layer graphene encapsulated in boron nitride by using this nano-optical tool, and that was pretty cool in our opinion. So take-home message here is that I believe that this tool is going to be extremely relevant in the future to probe, as we tried to do here with a weakly correlated material, but it's going to be a very useful probe to access, strongly correlated physics, in particular measuring quantities that were very difficult to access with other tools. So the full frequency and wave vector dependent conductivity, the so-called non-local conductivity, which I will flash in a few slides. Okay, and just to see how important non-local effects are in a simple graphene layer, in particular when the nearby gates are at 5, let's say, nanometers away from graphene, you can look at these plots where the black circles are, of course, experimental data, and the color-coded map is the full theory, including non-local effects, while the simple local RPA, namely the approximation in which you use just the local conductivity sigma of omega, performs very poorly. But I will mention these later with more detail. Okay. So let's now enter into the main part of the talk, and let's see what we expect for when you apply this nanoscopy tool to twisted bilayer graphene. I will show you, will try to convince you that there are fundamental differences with ordinary, simple, trivial intraband plasmons. The collective modes you excite are interband modes, and which carry very useful information, in our opinion, on the remote bands, and so that's what I wanted to convey. So we were motivated by these experiments carried out at ICFO by Frank, and we tried to help out with Jacopo and a number of other theorists in understanding these excitations. So this is a SNOM map done on twisted bilayer graphene. These are ambient conditions experiments, so room temperature, close to charge neutrality, twist angle 1.35 degrees, and illumination wavelength of 219 milli-electron volt. You see these very inhomogeneous distribution here of the optical signal, which I'm plotting here in the color bar, and I'm sure Niels discussed the experimental details of these in great detail. But essentially, you see patches of near-field optical activity, where the optical signal shows interference fringes pretty much like the interference fringes, I was showing the simple ones in the case of intraband graphene plasmons, but they are localized here in patches, which are in fact let's say, separated by patches where the optical signal is negligible by these circularly shaped profiles. So I will come back to these inhomogeneous distribution of near-field optical activity later on, but you see fringes, right? And so you see fringes and you would like to analyze them, and that's what I'm going to talk about. So how do you analyze this? Well, first of all, experimentally, you have a number of tools. Before thinking about electrical field effect, you can change the wavelength, you can change the probe wavelength, and check and how these fringes change with changing excitation wavelength. By the way, this was the same trick that was used to probe the simple graphene intraband plasmon dispersion, because in theoretical physics, like omega as a function of wave vector in plane wave vector q, and does not people do the other way around. They like to measure at the real and the imaginary parts of the plasmon wave vector as a function of illumination frequency, illumination energy omega, and so that's what they were able to do. And I'm sure that Niels discussed about details of this fitting function here to analyze the data. And from this data, the main message is that you can extract the real part Q1 and the imaginary part of the collective mode, yet unknown collective mode, of the two-dimensional electron liquid in twisted bilayer graphene at that particular twist angle. But how do you analyze profoundly these data experimentally? Okay, we do run immediately into a theory problem, right? So you know, we have a Moiré system, and as we have heard many times, we have a Moiré lattice, so you don't have anymore a very simple, effective low energy theory, which is Galilean invariant. And so you have to work effectively from all points of view, like if you were dealing with collective modes in a crystal. So in this case, you have to use the full theory of linear response in the case of inhomogeneous systems, with a simplification here. Essentially, the proper density response function, in theory, in a generally inhomogeneous system, would depend on two wave vectors, q prime, and the illumination frequency omega. But you know, excitations here can exchange only a wave vectors that differ at most by a reciprocal lattice vector. And so that's the way usually the density response function is written in a crystal. Is a function of q spanning the first Brillouin zone and two wave reciprocal lattice vectors GG prime. So it's formally a matrix in the space of reciprocal lattice vectors. And you have a generalized relationship between the proper density response function and the conductivity. You know, this equation in the translational invariant case was not shown in the previous slides, but it will be particularly useful here. And in fact, it's liked a lot by the people that do nanophotonics, because you have an immediate connection between an obscure object, that's infinite sum of Feynman diagrams, and something which can be measured potentially, which is the conductivity. But you see that in this relation, in general, you have the non-local conductivity, which also depends on Q and two reciprocal lattice vectors. Depending on the crystal symmetries, you may not end up be very lucky. And so you have to work with the full tensor in Cartesian indices, alpha, beta here. And plasmons, or let me say it better, collective excitations in the density channel of the electron liquid are zeros of the dielectric function epsilon, which is itself a function of q omega and matrix in reciprocal lattice space. Now, it's very, instead of looking at zeros of this, which is a matrix, you know, there is a much more powerful tool to look at collective charge excitations in a crystal. And that's essentially inspired by electron energy loss spectroscopy. In fact, people usually look at the so-called energy loss function that tells you how much energy is absorbed by the electron liquid for an excitation carrying momentum q and frequency omega. And that's the imaginary part of the inverse dielectric function viewed as a matrix in GG prime indices, and you select at the end, after you take the inverse of epsilon, you select only the G equal G prime equal 0 components. And then, so this allows you, by looking at peaks essentially rather than zeros, by looking at peaks in the energy loss function, you are able to identify collective modes, okay? So this is, general framework for a crystal. You know, it's quite cumbersome, and, you know, calculating non-local conductivity is difficult. And as I said, you know, to understand and grasp a little bit the physics of this complicated experimental data, we took a very simple approach using the so-called local approximation. So the local approximation amounts essentially, in the crystal language, to neglect off-diagonal components of the dielectric function in reciprocal vectors GG prime, and taking the local limit, the long wavelength limit in the conductivity sigma. So when you do this, you do the matrix inversion, which at this point becomes extremely easy. You can recast the energy loss function in terms of two ingredients, essentially. The local conductivity sigma, which becomes a scalar here because of the D3 point group symmetry of the crystal we're working with, and L of Q and omega is in general the Coulomb potential between carriers in twisted bilayer graphene, as screened both at, as screened also dynamically, but nearby dielectrics. So for example, you know, very well that HBN, nearby HBN, in the mid-IR where these experiments were carried out, is interesting optical activity. And so in general, if you want to look at and really model the experiments, you have to be careful about finite thickness effects, including phonon polaritons in HBN and the coupling between phonon polaritons and the collective modes in the electron liquid. And so you have to be careful, but everything is encoded into the electrostatics of the problem, okay? So the idea is that, you know, theoretically then you just have to be careful about these two ingredients, the local conductivity as a function of frequency, of course that's as a real and an imaginary part, and the Coulomb, the dressed Coulomb potential. So the idea is that by measuring, you know, let's say the real part of the plasmon wave vector, which is, you know, we know that is, you know, very reliable, extracted from the experiments in the way I was showing you, you can actually access the imaginary part of the conductivity. So the idea is that we have now all the theoretical tools and to calculate the local conductivity as a function of frequency, and then compare theory with the experiments. So historically, I will show you what we did in this paper, and then in a later PRB, which is going to appear soon, we studied all parameter space, changing the twist angle and band structure parameters, and so on and so forth. But let me tell you historically the gist of the physics, okay? So the gist of the physics is the following. When you do this procedure of having a Q and omega, you can invert that relationship and plot a good old dispersion relation, energy of the collective mode as a function of the wave vector Q. And you know, the two traces were taken spatially along the samples, and so we have two sets of data, many more in the supplementary material, but this is quite representative at the same twist angle that I was mentioning earlier, 1.35 degrees. And so you see a very weird thing. You see a mode which disperses linearly. For example, look at the blue data, which have a nice straight linear dispersion, which would extrapolate to a gap for a small wave vector Q, a gap on the order of, let's say, 300 MeV, and with a group velocity which is substantial. In fact, is much larger than the earlier papers predicted, the early papers on twisted bilayer graphene optics that I was showing earlier. Okay, and by using the denominator, by essentially finding the peaks of the loss function, you can relate Q of omega or this extracted dispersion relation with the conductivity. So there are two traces here for the imaginary part of sigma, the frequency dependent conductivity. There are two traces here that we are plotting, two sets of data, and then some attempted fitting. And so I would like to discuss this fitting with you of the imaginary part of the conductivity, okay? So, you know, the simplest thing you can think of is do some very simple Drude model, as every guy doing plasmonics would like to do, and this doesn't work at all. These are the dashed lines which provide you a very, very poor fitting of the data, right? And so we instead try to fit this data with a resonant profile, which is written here in the slides, in which the imaginary part of sigma in units of the conductance quantum 2e squared over h contains two fitting parameters: the position of the resonance in the denominator, omega x, extracted from experiments, and
sorry, Marco. There is a question from Jose Pizarro.
Yes.
And so I try to unmute you so you can ask the question. Allow to talk. Yeah. So in principle.
Can you hear me now?
Yes. Yeah.
Yes.
Okay. So my question is related with this approximation of taking the dielectric matrix, only the G equal G prime equals 0 matrix elements. So how is there any justification to calculate this, to consider this for twisted bilayer graphene, or
Well, I don't have any formal justification. I can tell you that we quantified, and I don't know whether there is honestly a section in the supplementary material, but we quantified the first order non-local contributions, and they were really, really small. But honestly, I'm, too new to this field to give you a very profound answer of why non-local effects are, at least in this particular range of parameters, are not very important. But I can check mathematically. I can tell you that we checked and they were small, at least the first non-local correction.
Okay. Thank you.
Thanks. Okay, so and the other fitting parameter is spectral weight. The spectral weight of these resonance profile, and of course you can calculate very simply analytically the Kramers-Kronig transform of these in sigma, finding the real part of the conductivity. It would be a delta function peak located at the position of the peak with a weight which is exactly omega exp. And the extracted parameters, as I said, are position of the peak on the order of 180 millielectron volts and spectral weight on the order of 300 millielectron volts. Okay, so these are the information that you find from these very simple resonant fitting functions. So I will try to convince you that where this resonant profile is coming from, and what is the level of agreement that you can establish between theory and experiments. Okay. So the first thing we did was use, realistic band structure calculations, and results that were provided to us by Stephen Carr and Kaxirax. And so state-of-the-art band structure, single particle band structures, and we were able, by using Kubo formula, we'll show you the equations later, we were able to produce just the real part of the conductivity as a function of frequency, which is here plotted in a black solid line. And in the inset, you see how these theory for the conductivity relates with the experimental data, which are the red circles and the blue circles. Okay, so we were not satisfied. By these, and we played then a little bit with a simpler two-band model. I will discuss later technical details. But since you have seen Vishwanath talk, we used I believe when we were working on this, we saw his preprint on the archive. We liked very much the chirally symmetric continuum model, and I've seen that you now know wave functions for the manifolds of flat bands. So it's contains only one parameter, because one U0, the intra-sublattice, the AA intra-sublattice interlayer tunneling is set to 0 in this parameter, and you have this extended symmetry. And by our surprise, just by doing exactly the same Kubo formula calculation of the real part of the optical conductivity, we were able to obtain a much better fit of the experimental data for the so you see how now the red data so the inset is of course for the imaginary part of the conductivity, which is directly extracted from the conductivity. We were able to fit in a much better way the data. Okay, so but there must be, so this resonant profile here, you can clearly see a very nice structured peak in the real part of the conductivity that absorbs a substantial fraction of the spectral weight. In fact, 162 millielectron volts, and in much better agreement with the data, also the position of the peak. And so we were wondering, how come? So a realistic band structure calculation gives you those results, and a completely idealized model, that needs to be handled with great care. You have to include perturbations if you wish, but this idealized model, very elegant idealized model, gives you a much better result. So the truth must be in between, but this already points to some very interesting physics. So we have to understand where this peak is coming from, that gives you this resonant profile in the imaginary part of sigma that then justifies the fitting function we have used. And we have to understand how these data depend on on microscopic parameters of the model. So we did a scan at that point, changing essentially the AA interlayer coupling, fixing U1 at the value predicted by state-of-the-art band structure calculations, 97.5 MeV, if I'm not wrong, and we scanned U0 all the way from the Bish-Van Aert limit, that was also exploited by Paco and collaborators back in 2012. From U0 equal 0, we scanned all the way to U0 equal U1, which represents the Bistritzer-McDonald limit, if you wish. And you clearly see that the position of these resonant peak changes with frequency monotonically, and the best fit of the experimental data extracted by Niels and Frank and co-workers was obtained for an intra-sublattice tunneling U0, which was on the order of 40 MeV, so substantially smaller than U1. And the spectral weight instead has a non-monotonous dependence on the temperature, and again it peaks some value in between the chirally symmetric continuum model and the Bistritzer-McDonald U0 equal U1 model. I will define those parameters later, okay? So that was, enough for an experimental paper. We wanted to dig a little bit better into this. Predictions, also including a number of other effects, which I'm going to mention. Okay, so let me begin with the Hamiltonian that you have seen over and over these days. So the Hamiltonian contains ordinary intralayer terms, H1 and H2, and interlayer, very subtle tunneling terms that are parameterized by these U0 and U1 parameters, physically representing respectively the intra-sublattice AA tunneling rate and the inter-sublattice ABBA tunneling rate. And so in the original BM model, U0 was taken to be equal to U1, and it has already been pointed out by a number of people, Coscino, Caxira, Xcar, I reported a few references here in this slide. I apologize for the others I've not cited, but has already been noticed in the literature that there is no reason for U0 to be equal to U1, and in fact, if you account for relaxation and other effects, you can typically tend to have U0 smaller than U1, but so essentially the main point I want to convey is that carrying out a detailed experimental study of the dependence of these optical conductivity and the collective excitations with respect to the ratio U0 over U1, you are able to extract experimentally for that particular sample. It may vary from sample to sample the actual value of these parameter U0 once you fix the other one, let's say. So we believe that you gain very useful information by carrying out these optical studies. And finally, we also again repeated these calculations of the local conductivity by studying this chirally symmetric continuum model, setting U0 equal 0. Okay, but as Alan mentioned, and many other people, and Paco stressed this a lot back in 2018, it's very important in these systems to include a screening, let's say, in the sense that there is because of the moire, there is a highly inhomogeneous charge distribution, and you have to calculate the density self-consistently in order to make sure that screening of the electron system is taken properly into account, and this has an impact of course, on the band structures. Many people have stressed recently. So we wanted to include also this effect by carrying out both single particle calculations and self-consistent R3 calculations, time-dependent R3 calculations, combining these R3 calculations with RPA later to look at the conductivity, and those essentially are the results of this PRB, which is going to be posted soon. And so for the students in the for the students in the audience, so you have to write down the R3 potential, which I wrote in real space a few slides ago, and it's written here in Fourier space. This contains in general a sum of the reciprocal lattice vectors that we truncated to the first shell we truncated to the first shell simply because the Coulomb potential decays with 1/g, and we took into account for these calculations, we just neglected all these, you know, complicated effects due to phonon polaritons in HBN, because I would like to show you now, while those were included in the experimental paper I was trying to tell you about a few slides ago, in the next few slides, I will neglect this complete, let's say, not fundamental question. I would like to look really at collective excitations and give a physical interpretation in the absence of these complicated extrinsic effects due to the presence of HBN. Okay, so you have to, you know, calculate, you know, solve this eigenvalue problem. Clearly, this depends on the density, and so you have to solve until self-consistent is reached. And as I've been discussing with Alan several times, and I'm trying, you know, to digest these, you have to be very careful in doing these, and so you have to check that you include a sufficiently large number of bands in your self-consistent calculations to make sure that everything is done properly. And so we believe that we have been very careful about that. Okay, so once you know new eigenvalues and eigenvectors, you can use essentially Kubo formula. Now I don't know how much time I have, but perhaps Adrian, you can tell me.
Yeah, so you started 55 minutes ago. So,
oops, okay. So I will wrap up very quickly. Yeah, sorry. So we used the ordinary Kubo formula to calculate the Drude weight for the intraband conductivity and the standard ordinary interband Kubo formula for the interband contribution. And again, because of the D3 point group symmetry, these alpha beta Cartesian indices are totally irrelevant. And you can do these calculations both at the bare level or the bare of the self-consistent R3. Okay, so let me discuss the, well, you know, Paco has already, and Alan has already discussed these quite a bit. You have substantial effects due to rearrangement in real space of the ground state density profile, which has a large impact on the manifold of, you know, flat bands, giving you this, you know, upward bending that you clearly see here at the gamma point. And you know, can calculate these quantities for a variety of filling factors and, you know, different parameters. And we calculated the Drude weight, noting that there is an enlarged particle asymmetry, which is included when you do self-consistent R3. And however, I'd like to go to the you know, main results, since I don't want to take a lot of time from you. Okay, so here I'm plotting the results for the real part of the conductivity, essentially, as a function of frequency and as a function of filling factor. The other parameters have been fixed. So this particular slide is for U0 smaller than U1 and theta being 1.05 degrees. So, you know, one thing that you clearly see immediately is that essentially near a very low energies, there is a peak, a very weak peak due to transitions in the manifolds of flat bands. But as you approach 40 millielectromoles, there is a very sharp peak, which is due to transitions between the manifold, between the, you know, the valence flat band and the first conduction band in the remote bands. And then, you know, later there is, at higher energy, there is another transition, this time coming from electrons near, from states near the K point rather than the gamma point. So the real part of the optical conductivity carries this very useful information on the remote bands, as I was saying. And these are our results for the collective modes. So the essence is that associated with this large peak in optical absorption, there is a collective excitation in the density channel, which has a linear dispersion as seen in experiments that we interpret as an interband plasmon, but the jargon is very poor, of course, because as you know very well, in these electron-hole transitions, there are large excitonic electron-hole attraction effects. And so in order just to be sure, we would like to carry out, to include essentially excitonic electron-hole attraction effects by doing a time-dependent R3-Fock calculations later on to see how the results change compared to simple RPA. This is probably the most important slide that I wanted to show related on this PRB paper, which is going to post to appear soon. Essentially, it's the same thing. It's the real part of the optical conductivity, this time plotted, of course, as a function of frequency omega, but also as a function of U0. So we fix U1, as I said, at 97.5 MeV, and we scan the value of the intra-sublattice tunneling rate, U0 at the magic angle 1.05. And so you see that the main peak associated with the transitions, interband transitions at the gamma point and at the K point, the two main peaks you see in the real part of the optical conductivity, they are extremely sensitive and downshift quite a bit when you increase U0. And this is the point that I was trying to make earlier, that, you know, we bumped into accidentally by playing with the Vishwanath model, but we do now understand quite well, at least within this simple local theory and time-dependent R3 approximation, we clearly see that there is a high sensitivity both of the real part of the optical conductivity on the value of U0, but also on collective modes. In fact, the profound reason why the group velocity of these interband plasmons is much higher than previous works on optical properties of twisted bilayer graphene, it's precisely a reduced value of these intra-sublattice. So in other words, when U0 is substantially smaller than U1, the group velocity of these interband collective excitation that we find tends to be higher and in very, very good agreement with the experimental data. And of course, you can also study the dependence of twist angle, but you know, and also the optical properties as, you know, transport and everything else. It's quite sensitive to the twist angle. But I don't need to say that to this audience. So let me conclude here with a summary, because I took too much time. Essentially, the main message of this talk, I hope that I conveyed, is that, you know, we strongly believe that far field and near field optical studies of twisted bilayer graphene are very sensitive to the interlayer tunneling energy scales and to remote bands. And so details of the band structure at the gamma point, which are particularly relevant, also to put into the theory of broken symmetry states and in your single particle Hamiltonian. So we feel that these are this is precious information that should be used in the many-body studies. Of course, far-field studies probing directly the optical conductivity would be also desirable, but we know that those require large samples, and so, you know, the quality of the samples is not so great, and, you know, large samples are yet unavailable. So, and in general, even if you would have large samples, we have seen from the talk of Elie Zeldorf that you would be probing quantities averaged over distribution of disorder in the twist angles. So we feel that this near field scanning, you know, optical studies with real space resolution really offer a unique opportunity to really probe both the local and the non-local conductivity together with the collective modes and like these interband plasmons that I was talking about. And the dream is, of course, and many people is working on this, is that you could do, you know, setups like cryosnom working at low temperatures are beginning to be available in the community. So eventually, you know, hopefully in the near future, they will also thrown at twisted bilayer graphene to probe collective excitations. And so theory-wise, as I said, and Alan has already something about that I mentioned during his talk, it's, you know, it's important to include electron-hole attraction effects. And so we are setting up a time-dependent R3-Fock theory to look at these collective modes and how they depend on the ratio U0 over U1 and twist angle and so on and so forth. And one mystery remains, however, I didn't, you know, go back to this. Is so, you know, why the hell these samples display these patches of near-field optical activity together with patches where the optical signal is not there. And, you know, I should have said, I'm sure Niels did a much better job than me in saying that these patches are sensitive to AFM brooming. So you know, so if you, once you fix your procedure and you broom the device, then you scan wavelength, of course, nothing bad happens. The collective excitations are there, extremely robust and change in a sensible way with the excitation wavelength. But, you know, if you broom then the device, the patches of near field optical activity, you know, move around. So, you know, gotta be careful about that. And we don't have yet, at least I don't, very simple. I don't have not even a complicated explanation of these patches of near field optical activity. And however, the fact that there is this geometry of you know, circular geometry that divides the patches of near field optical activity from those where the signal is not there. We were speculating with Jacopo, perhaps, you know, maybe a sign of fundamental coexistence between different phases, although the experiments were done at room temperature, so it's hard to conceive, you know, also these scenario at the time being. So really, thank you very much for your attention, and you know, I would like to acknowledge also the funding that brought us here, and thanks a lot, and sorry for taking too much of your time. Yeah.
Thank you very much.
Grazie.
And so there is a question from Jonathan Ruman, and I will allow you to talk. Can you ask your question, Jonathan?
We see Jonathan, but we don't hear. Well, there is a delay usually.
Okay, I think you can speak now. You're unmuted, Jonathan.
Jonathan says he doesn't have a mic.
Okay, so
yeah, he cannot talk.
So why is the feature of the interband in the absorption so weakly dependent on momentum?
So weakly dependent on momentum. Well, you know, I don't know. Well, in the real part, I mean, of the conductivity is taken in the local limit. So just a sigma of omega, and the peak is changing only with omega when you change system parameters. But in the interband dispersion, there is, I mean, these are propagating interband plasmons. Now, I would probably flashed too many results and created a confusion. But as you see, the lower U0, I mean, these interband modes are propagating. And in fact, in the experiment, they form interference fringes. So there is a wave vector dependence of these modes, but is displayed by the energy loss function, which are the color plots I'm showing. So sorry for creating confusion about that. Yeah.
Okay. So as an experimentalist, so it's a question for me now. So as an experimentalist, you have different tools. So for example, you can apply a magnetic field. You can also change the devices, for example, making bilayer twisted devices. So to test your theory, in which direction should experimentalists go?
But I don't know, already, you know, Frank and Niels in the archive paper that I cited, they in fact even tested a double bilayer device. And they saw these interference fringes, collective modes also in that device, but we don't have yet a theory, a microscopic theory like the one Paco was showing, for example, a few days ago on twisted double bilayer and their optical properties. But well, clearly, I would like to see, as an experimentalist, I would like to see electric field dependence, of course, of these modes. I mean, in graphene, that was absolutely pivotal, you know, gate tunability, and check fundamentally how these, you know, interband modes, how they depend on density. So that would be ideal. So the experiments I was showing were carried out only at charge neutrality points. So I'm sure Niels and Frank and, you know, Pablo, they are working very hard to have devices where you can do both AFM, SNOM, and electrical field control of the electron density. So before applying any magnetic field, that's what I would do. Yeah.
And there is a question from Gen Lee. So if you ask a question, can you then also raise your hand, because now I have to find you in a long list of people. Okay, I have found you. So I think, Gang, you can speak.
Oh yeah, well, my question is, for the loss function of twisted bilayer graphene, it seems it's only related to its optical conductivity. So why is not related to the instant electron energy or direction or the optical source type, either plane wave or dipole source?
Sorry, I'm not sure. Can you repeat the question, please? Or perhaps Adrian, can you, because I had a poor. So
Again,
I mean, oh sure. For the loss function calculated from the optical conductivities of twisted bilayer graphene for the plasma, it seems that loss function is only related to its O property, not related to outside excitation like instant electron or dipole source or plane wave. Why it's not related to those sources?
Well, I mean, the idea of linear response theory, I mean, in this case is that your source care is a finite Q and a finite omega. And that's the only thing that enters. I mean, if you would like then to really, you know, analyze a serious source, you have to make a convolution with the source you're making. But the idea of linear response theory is that you study the response to a single plane wave oscillating in time with e to the minus I omega t, e to the I q dot r. And if you are in the linear response regime, just by knowing the response to a single plane wave, then you can do everything you like, depending on the source that you want. So that's why we theorists in linear response theory, we just analyze the response to a single Fourier component. And that's it. And then we hope that if the experiment really needs, we can sum up the contributions and use really the line shape of the excitation. So
thank you for the answer.
Okay, there is a question from Christian Novokovsky. So I allow you to talk. In principle, you can speak now, Christian. Christian?
he's still muted, I think.
So it doesn't unmute. So it's better to press once and wait a long time, or press several times every 2 or 3 seconds?
You are the experimentalist.
Otherwise, I read the question. What could explain the smaller U naught? In transport, they extract U naught. Here it's different. What could explain the difference?
But we speculated in the archive paper. We speculated. So I like this paper by I think Paco was the first probably in in 2012 to speculate that U0. So you can view these bands as as essentially stemming from an electron moving in a background scalar and non-abelian gauge field, right? So U1 is responsible for this non-abelian contribution, and U0 is instead responsible for a U0, right? So despite they are so in this language, I would tend to think, but I may be wrong, that, you know, as in the historical theory of graphene, scalar potentials tends to be screened efficiently, while you know, essentially gauge fields are not screened. So I was you know, speculating that U0 tends to be can be substantially smaller than U1 just because of screening. So an electron-electron interaction contribution that you know, reduces the value of U0 compared to U1. So, but it's pure speculation, honestly. So.
Okay, thank you. And now the last question from Muhammad Avisine Naradipa. I allow to talk. And normally you unmute now.
Oh, hi, hello.
Hello.
I just want to ask if we are doing optical calculations from DFT based, for example, if we do GWBSC or something like time-dependent DFT, will these results be reliable after reading your results from these calculations? And how does it compare with the RPA and the local field effects from these calculations?
Well, you know, as you know, I mean, you know, for small twist angles, it's impossible to apply brute force DFT. So you have to do, you know, something like along the lines of what has been discussed in these symposium, including perhaps exchange, which is very important. Otherwise, you know, you don't get any broken symmetry phases. But the good, honest answer is that I don't know. I mean, but perhaps, I mean, we could do some benchmark calculations at larger twist angles where ab initio many body theory can be applied, and then compare the results, honestly. So I come from a weakly correlated community where these approaches are extremely you know, work fantastically, but of course these are completely different systems. God knows how this approximation is going to work. We already know that the exchange contribution is very important, even in simple graphene, because of velocity renormalization, and here for broken symmetry states at low temperatures near the magic angle. So I don't know, but it's a good suggestion. Perhaps we could benchmark the results against you know, serious ab initio DFT large twist angles. Yeah.
Okay. Thank you very much.
Okay, so thank you very much, Marco, for this interesting talk. And now there is a break, and at 6 o'clock there will be the presentation from Tobias Rudel from Nature. And so for those, please join us at 6.
Okay,
Goodbye.
bye-bye, Adrian. Ciao, bye-bye all. Thanks.
Okay, thank you very much. I'm gonna end the meeting now, and I will see you in the Q&A with the Nature editor, starting 6 p.m. Thank you.